Polynomial functions and their graphs. A polynomial function of degree n is a function p of x equals a n x to the n plus a n minus 1 x to the n minus 1 plus etc. all the way down to the last term a0, which is actually pronounced a naught. Now these a values, these a n's, are the coefficients of the polynomial, and they're written in such a way that the subscript of the coefficient matches the degree of the term. So for example, an is the coefficient of the x to the n power term, and we do this for convenience. Now the number a0, pronounced a naught, is the constant coefficient, or sometimes it's just called the constant term. The number an in the front here is the coefficient of the highest power and is referred to as the leading coefficient. And an x to the n is the leading term. So for example, if we have a polynomial 3x to the fifth plus 6x to the fourth minus 2x to the third plus x squared plus 7x minus 6, let's just take note of the fact that the leading coefficient is 3, the degree of the polynomial is 5, the constant term is negative 6, the leading term is 3x to the fifth, and this polynomial has 6 coefficients, and those 6 coefficients are 3, 6, negative 2, positive 1, positive 7, and negative 6. Another thing we should note about polynomial functions is that we typically like to write them in descending order. That means we like to write them from the highest power of x and then decreasing down to the lowest power of x. And the constant term technically is x to the 0. So sometimes that is called the 0 degree term. Now, before we talk about graphs of polynomial functions, let's go back and remember the graphs of our basic power functions, which are also called basic monomials. Now, a monomial simply means a polynomial that only has one term. So for example, y equals x to the 1, y equals x squared, y equals x cubed, y equals x to the fourth, and y equals x to the fifth are all examples of basic monomials. And you'll notice that these are polynomials of degree 1, 2, 3, 4, and 5. Now we talked about these functions in a previous video, and what I want to reiterate here is that you'll notice that the even degree monomials both behave similar to each other, and that is that they go up on both sides of the graph. And then you'll notice that the odd degree monomials here go up on one side and down on the other side. And that's consistent for all of these graphs. And you're going to see something similar to that in the graphs of polynomial functions. First, let's talk about transformations of monomials. So given the graphs that we just looked at, how could you graph something like p of x is equal to negative x cubed? Well, you would need to remember that putting a negative in front of a function will reflect the graph over the x-axis. And so if this graph here represents y equals positive x cubed, so I'm talking about this graph right here, then negative x cubed is just going to be the reflection of that graph over the x-axis. So this part down here gets reflected up here, and this part up here gets reflected down here. And so this graph right here would be the graph of p of x is equal to negative x cubed. Next, we have q of x equals x minus 2 quantity to the fourth power. So we know that y equals x to the fourth power. Looks like this graph right here. And so x minus 2 quantity to the fourth power is just going to shift this graph to the right 2 units. Other than that, it has the exact same shape. And finally, negative 2x to the fifth plus 4 is going to take the graph of x to the 5th power, which looks very similar to x to the 3rd power. The negative 2 is going to reflect it over the x-axis, so that graph will look something like this. And then the positive 4 here is going to shift the graph up 4 units. And so the graph of negative 2x to the 5th plus 4 would look like this one here. Now let's discuss the basic graph characteristics of polynomial functions. Polynomials are really nice graphs. So graphs of polynomials are smooth and continuous. So if you look at these two pictures here, you'll notice that each of these graphs are smooth and continuous. There are no sharp edges, there are no breaks in the graph, they are just nice and smooth and continuous. And you can see they both behave the same in that regard. So graphs that have breaks or holes or corners or sharp points on them, those kinds of graphs cannot be the graphs of polynomial functions. So the thing that we like about polynomial functions is that they are nice and smooth and continuous. Now, once we get past that, we need to figure out some other things about polynomial functions. For example, we know they're smooth and continuous, but how do we know about the shape of the graph? What makes it have these peaks and valleys like you see here? So before we discuss that, let's talk about some symbolism. So when we use the symbol x and then an arrow and then infinity, what we're saying is that x goes to infinity. And that means that x is increasing without bound. So x is getting larger and larger and larger. When we write x and then an arrow and then negative infinity, we are simply saying that x goes to negative infinity, and that is x decreases without bound. So now what that means is x is becoming a larger and larger negative number. This is very useful in describing the behavior of polynomial functions. So if you consider the graph that you see here, what I want you to notice is that on this graph, as x is getting larger and larger, so over on this side of the graph, we would write x is going to infinity. You'll notice that this part of the graph also has the y values going to infinity, right? In other words, as x is getting larger, y is also getting larger. But on the other side of the graph over here, as x goes to negative infinity, you'll see that the graph is going down forever. And that means that y is also going to negative infinity. So when we use this kind of symbols, what we're talking about here is describing the end behavior of the polynomial. So let's discuss that in a little bit more detail here. The end behavior of a polynomial function on its graph basically refers to what is happening at the outer edge of the graph. So we're not too much interested in about the humps and the valleys in here, right? We're not worried too much about that. We're talking about what's happening at the extreme edges of the graph. So there are basically two cases. You can have an odd degree polynomial, or you can have an even degree polynomial. If you have an odd degree polynomial, what you will notice is that the graph will go up on one side and it will go down on the other side. So for example, as x goes to positive infinity, y also goes to positive infinity. And as x goes to negative infinity, y is going to negative infinity. Or the opposite can happen, meaning it could go up on the left side and down on the right side. In this case, we would say as x goes to positive infinity, y goes to negative infinity. And as x goes to negative infinity, y is going to positive infinity. For even degree polynomials, it's a little bit more simple. For an even degree, it's going to do the same on both sides. So it either goes up on both sides or it goes down on both sides. And to say that mathematically, we can say y is going to positive infinity as x is going to positive infinity, and we can say y is going to positive infinity as x is going to negative infinity. Or in this case over here, y is going to negative infinity as x goes to either negative infinity or positive infinity. But knowing the end behavior of a polynomial will help you graph the polynomial function. Finally, the other thing to note about this is what determines whether it goes up on both sides or down on both sides, or the difference between these two graphs over here, is the leading coefficient of the polynomial. So if the leading coefficient is positive, we have this behavior, and for even degree, we have this behavior. And if the leading coefficient is negative, for odd degree, we have this behavior, and for even degree, we have this behavior. Let's take a look at an example. So let's determine the end behavior of the polynomial p of x equals negative 2x to the fourth power plus 5x to the third power plus 4x minus 7. So first, let's just take note that the highest power is 4, so this is an even degree polynomial. And let's also notice that the leading coefficient is negative 2. So it has a negative leading coefficient. So how is this going to behave? Well, we know that when the degree is even, it's going to either go up on both sides or down on both sides. But since the leading coefficient is negative, this polynomial is basically going to behave in this manner. Now, we don't know what the behavior is going to be in between those two extremes, but we know that on the extremes, it's going to go down in both directions. So the way we would describe this is we would say y is going to go to negative infinity, which basically just means it's going down, as x is going to positive infinity, which basically means to the right. Okay, so we're just describing this part of the graph right here, right? As x goes to the right, y is going down. And then on this side, we can say y is going to negative infinity, which again means down, as x is going to negative infinity, which of course just means to the left. And so as x is going to the left, y is going down. So this is the technical way that we would describe the end behavior without drawing a graph. Of course, a graph is always nice though. And here is a picture of what this polynomial graph would look like. And you can see we have the notation here as we just previously put on the screen. But this is the end behavior. You can see that indeed it is going down on both sides. Let's take a look at the end behavior of the polynomial p of x equals positive 3x to the fifth power minus 5x cubed plus 2x. So again, we have the degree of the polynomial. In this case, it's odd. And the leading coefficient is positive, right? It's greater than 0 because the leading coefficient is positive 3. So when you have an odd degree polynomial with a positive leading coefficient, we know that the end behavior is going to be up on the right side and down on the left side. And again, in between, we could have all sorts of different kinds of behavior, but we know that on the extremes, this is what it's going to do. So again, what I can say here is y is going up as x is going to the right, and y is going down as x is going to the left. Now for part B, let's go ahead and graph this polynomial, and also let's graph the polynomial that is just the leading term here. And we want to show that the same end behavior exists for both of these graphs. So let me go ahead and bring in a couple of pictures. So here is a picture of P, the polynomial you see here, which is this red graph, and Q, which is the simple graph 3x to the fifth, which is this blue graph here. Now, on this window, with x between -1 and 1 and y between -1 and 1, you really can't see the end behavior because we're too zoomed in. So if we zoom out just a little bit, if we just zoom out one more unit in both the x and y direction, you'll start to see that the polynomial p of x, which is this graph here, and the polynomial q of x, which is 3x to the fifth, which is this graph right here, you can start to see the end behavior is the same, can you not? You can see that it is going up on both sides here, and it is going down on both sides here. But what's very interesting about these graphs is that if you zoom out more, you'll notice that these graphs start to look like each other a lot more. Let's zoom out. So if we zoom out a little bit more in the x direction, one more unit, and if we zoom out a lot in the y direction, what you'll notice is that you don't really see the curvature of the polynomial p of x because we're too far zoomed out to notice it. But you'll notice that the end behavior now is really evident. These two polynomials have the same end behavior. And if you zoom out a lot more, so if we zoom out to negative 10 to positive 10 on the x-axis and negative 10,000 and positive 10,000 on the y-axis, you can hardly distinguish the two graphs from each other. You see that? They have precisely the same end behavior. So what I'm trying to point out here is that when determining the end behavior of a polynomial, this is why it's only the leading coefficient that matters. These terms don't matter at all in terms of how the polynomial behaves at the end, okay? These terms that you see here do determine how it behaves in the middle. So we know that the graph goes down on one side and up on the other, but exactly what it does between those 2 points, that is stuff that is determined from the rest of the terms. But the end behavior only depends on the leading term. To fully discuss graphing polynomial functions, we must discuss real zeros of polynomials. So if p is a polynomial and c is a real number, then the following things are equivalent. We say that the number c is a zero of the polynomial if x equals c is a solution of the polynomial equation p of x equals 0, and that is equivalent to x minus c is a factor of the polynomial, and the number c is an x-intercept on the graph of the polynomial. So saying any one of these 4 things is automatically saying the other 3. So if we're looking for zeros of polynomials, it's helpful to find the factors of the polynomial because the factors will tell you what the zeros are. And we know that the zeros also tell us about x-intercepts. Now, we discussed all these things when we talked about quadratic functions, but this is now just an extension to higher degree polynomial functions. Now, we also have the intermediate value theorem for polynomials, and this simply says if p is a polynomial function and p of a and p of b have opposite signs, meaning one of these is positive and one of these is negative, then there exists at least one value c between a and b for which p of c is equal to 0. Now let's briefly talk about why the intermediate value theorem for polynomials must be true. Suppose we have an x and y coordinate system here, and suppose we have some polynomial p of x, and let's say here is x equals a, and here is x equals b, and let's suppose that p of a is equal to this number, so we can see that p of a is greater than 0, it's a positive number, and let's suppose that p of b is equal to this number, and we can see that p of b is negative because it's below the x-axis. Basically, if I were to graph the polynomial, we know it has to go through this point and it has to go through this point. But we also know that polynomials are smooth and continuous. So let's suppose I'm graphing the polynomial and it looks something like this, okay? To get to this point down here, I'm going to have to cross the x-axis, aren't I? Right? No matter how the polynomial looks after that, to get from this point down to this point, we must cross the x-axis at some number between a and b. So that number between a and b is the number that we're calling c. And so that's what it means when it says there exists at least one value of c between a and b for which P of C is equal to 0. And remember, when we say P of C equals 0, we're basically just saying that there's an x-intercept at x equals C. So now let's talk about guidelines for graphing polynomial functions. The first thing we should always do when trying to graph polynomial functions is find the zeros of the polynomials. And really, we only care about the real zeros because only the real zeros show up as x-intercepts on the graph. Next, we should do some test points. So to do test points, we're going to make a table of values for the polynomial, and we're going to pick points in between the zeros. Finally, let's take a look at the end behavior so we know how the end behavior is for polynomials based on our previous discussion, and then we put all these things together and we can sketch the graph. So in this example, let's suppose P of x is the polynomial in factored form, x plus 2 times x minus 1 times x minus 3. Now we start with an example in factored form because when a polynomial is factored, it makes it very simple to see the zeros of the polynomial. So we know that P of x is going to equal 0 when x is equal to negative 2, right? Because negative 2 will make this factor 0. Also when x equals positive 1, which makes this factor 0. And finally, when x equals positive 3, which will make this factor equal to 0. So now what I'm going to do is put those numbers on a number line that you can see right here, and then I'm going to test the polynomial at points in between these zeros. So for example, in the interval over here, I can pick any number less than negative 2. Let's use x equals negative 3. If you plug negative 3 into the polynomial, let's do that real quick. So P of negative 3 would simply be negative 3 plus 2 times negative 3 minus 1 times negative 3 minus 3. And this is equal to negative 1 times negative 4 times negative 6. And I don't really care too much about the value here, but I do care if it's positive or negative. Now 1 times 4 times 6 is 24, but a negative times a negative times a negative is a negative. So we can see that P of negative 3 is less than 0. It's negative. So on the number line here, we have P of negative 3 is negative. Now we do the same thing for the next interval. So if I pick a number in between negative 2 and positive 1, for example, if we pick x equals negative 1, we can observe that P of negative 1 will be positive. In between 1 and 3, I can pick x equals 2, and we'll observe that P of 2 is negative. And finally, any number greater than 3, if I use x equals 4, this should say P of 4 is positive, okay? Now these test points tell us whether the graph is above or below the x-axis. So for example, when x is a number less than negative 2, the graph will be below the x-axis because the test point was a negative value. In between negative 2 and 1, the test point was positive, which means the graph will be above the x-axis. In between 1 and 3, it will be below, and to the right of 3, it will be above. So let's go ahead and bring in the graph now. So you'll notice that we have our x-intercepts at negative 2, positive 1, and positive 3. And then using those test points, we know the graph is going to be below the x-axis here, above the x-axis here, below the x-axis here, and above the x-axis over here. And finally, since we do know that this is an odd degree polynomial, right, because the degree is 3, and we know this because if you multiply x times x times x, you get x cubed, and it has a positive leading coefficient, so the end behavior is that it has to go up on this side, and it has to go down on the other side. So we can use all those things together to sketch a graph of this polynomial. Now, this is not necessarily going to give us a perfect graph, but it will outline all of the important behavior of the graph. Let's take a look at another example. In this case, P of x is not factored. So the first thing we want to do is factor it so that we can find the zeros of this polynomial. So notice that P of x has a common factor of x in all of its terms. So if I factor out that x, we have left over x squared minus 2x minus 3. And x squared minus 2x minus 3 is pretty straightforward to factor. It's going to factor into x minus 3 and x plus 1. And from here, if you set this equal to 0, we can see that x is going to be 0, 3, or negative 1. Now, how about the graph itself? Well, let's remember, if we put these numbers on a number line, now we can pick test points in between each one of these zeros. So for example, here I might pick a test point x equals, say, negative 5. Here I'm going to choose x equals negative 1/2. Here I'll choose x equals 1, and to the right of 3, I'll choose x equals 10. And we're just going to plug those in. Now I'll skip the work on this, but I'll just show you, for example, when you plug in 10, you're going to get 10 times 10 minus 3 times 10 plus 1, and that's going to be a positive number, of course. So when you plug in 10, you're going to get a positive. If you plug in 1, you will get a negative. Negative 1/2 will give you a positive, and negative 5 will give you a negative. Now also the end behavior, we have an odd degree polynomial, and we have a positive leading coefficient here. So we know the end behavior is going to be up on the right side and down on the left side. So I can sketch very quickly what this graph is going to look like by simply graphing the x-intercepts, which are negative 1, 0, and 3. And then we know that it must go up on this side and down on this side. So really in this case, the only plausible graph would be something that looks like this. Now that's not a perfect graph, but that is good enough, again, for describing the major features of the graph. And here is a nicer picture of the graph and also a nice table. And you can see that this is very close to the graph that I sketched just a moment ago. Let's do one more of these. So here we have P of x, and we want to first find the zeros. So once again, notice that we can factor out a greatest common factor. This time, notice that I can take out an x squared. And anytime your leading coefficient is negative, you should also factor out the negative. So I'm going to factor out a negative x squared. What we have left over then is positive 2x squared, positive x, and negative 3. Now let's work on factoring what's in the parentheses there. And again, you can do a magic x for this or however you like to do it. But in this case, it's not terribly difficult to factor. And now if we set this equal to 0, we're going to get x-intercepts of 0, negative 3/2, and positive 1. Now, let's go ahead and take a look at a number line, and we'll put these zeros on that number line. And then we're going to test. Now, I will skip picking test points. So you're going to pick numbers in each of these intervals, and you're going to plug them into the polynomial. And we'll simply observe whether the polynomial is positive or negative on those intervals. So here it's going to end up being negative. Here it will be positive. And then here it will also be positive. And over here it's going to be negative. Now let's think about what that means in terms of its graph. So we have a 0 at negative 3/2, we have a 0 at 0, and we have a 0 at 1. Now also keep in mind that since this is an even degree polynomial with a negative leading coefficient, we know that the end behavior of this graph must be down on both sides. So we know that the graph is going to go down in this direction and down in this direction. But if you think about it, how is it going to behave at the zeros? So if I go through this 0, and then I go through this 0, how's that going to be that I go through this 0 and go down? That's not going to be what happens there, is it? So there's something a little bit extra that's happening here. What ends up happening is we go through this 0, but when we come down to touch the x-axis here, we don't actually go through it. We do just a touch, and then it turns around again, and then it comes back down through this value. So what's happening with this graph is it's behaving something like this. And again, this is not a perfect picture, but this is the basic behavior of that graph. So the question is, how did I know that it was going to just touch the x-axis here, as opposed to these 2 points where it goes through the x-axis? And we know that from looking at the factors themselves. So if you go back to the factors of p of x, I want you to notice that here we have an even factor, right? X squared is an even factor. 2x plus 3 is raised to an odd power, so that's an odd number of factors there. And x minus 1 is also raised to an odd power. So when the power of a factor is odd, the 0 is going to be a pass-through type of 0. Okay, so this passes through, meaning that it's negative on one side and positive on the other side. Same thing over here, negative on one side and positive on the other side. But when the power is even at that x-intercept, it's not going to pass through. It's going to do a touch and turn around type of behavior. So let me go ahead and bring in a nice picture of this graph, and then we'll talk a little bit more about how you can test for that kind of behavior. So here is a nicer picture showing the 0 at negative 3/2, the 0 at 0, and also the 0 at 1. And again, you can see that it barely touches the graph, the x-axis, here at this particular 0. So the shape of a graph near a 0 of multiplicity m can be described as follows. If m is odd, then you're going to have a 0 that is a pass-through kind of 0. So it could go from below the x-axis to above the x-axis, or it could go from above the x-axis to below the x-axis, but it's going to pass through. If the multiplicity is even, then it's going to touch and turn around, and that could happen above, or it could touch and turn around below the x-axis. So let's go ahead and do this one here. Find the zeros and graph the following polynomial. P of x equals x cubed minus 2x squared minus 4x plus 8. So first of all, let's notice that there is no greatest common factor here, right? There is no number or x that can be factored out of every single term. However, I can factor this by grouping. So what I can do here is I can pull out an x squared out of the first two terms, which leaves us with x minus 2. And then out of the next two terms here, I can pull out a negative 4, and that's going to leave us with x minus 2 as well. And now notice that you have an x minus 2 here and an x minus 2 here. I can factor out that x minus 2, and then what's left over is x squared minus 4. Now, x squared minus 4 can also be factored. This is the difference of two squares, so it factors rather easily as x minus 2 times x plus 2. And now you'll notice that you have a repeated factor here. So we can write this as x minus 2 to the second power times x plus 2, and of course that's to the first power. So now that I have this polynomial factored, we can notice that the zeros of this polynomial are going to be positive 2 and negative 2. And so when I go to graph the polynomial function, we're going to have a 0 at negative 2, and we're going to have a 0 at positive 2. And then now the question is, what is it going to look like in terms of end behavior and in terms of the behavior at the zeros? Well, it's an odd degree polynomial with a positive coefficient. So that means we know it must go up on the right side and it must go down on the left side. But how does it behave at the zeros? Well, at x equals positive 2, notice that that factor has even multiplicity. So what that means is at this 0, it's going to come down and touch and turn around. And then at the other 0, at negative 2, which comes from the factor x plus 2, this has odd multiplicity, so this is going to be a pass-through type of 0. Also, let me just point out that the y-intercept for this graph is 8. If we let x equals 0, we get y equals 8, and that's going to be where it crosses the y-axis. So this graph must behave something like this. It comes down, it touches here, and it turns around. It has to go through the y-axis at 8, and then for this other 0, it is a pass-through type of 0. So that means it's going to continue in this direction. So again, this is just a rough sketch of the graph, but notice that we don't really have to plug in any points to get a good picture of the graph. So for this next polynomial function, we can graph it rather easily because notice that it's already in factored form. So we can list the zeros here. We're going to have zeros at 0, 2, and negative 1, right? Because that's the value of x that makes each of these factors equal to 0. That means when we go to graph it, it's going to cross the x-axis at 0, at positive 2, and at negative 1. Also, notice that the degree of this polynomial, if you add up these exponents here, 4 plus 3 plus 2 is 9. And we have a positive leading coefficient of 1. So we know the end behavior is going to be up on this side and down on this side. So now the only question is, how does it behave at the zeros? Well, we have even multiplicity here, and we have even multiplicity here. So that's at 0 and at negative 1. So for both of those, it's going to be just a touch type of x-intercept. So when I'm graphing this, when it's coming up here, it's going to have to touch and turn around, and then it has to go back up again, and it's going to touch and turn around again, and then for this final one, it's going to be a pass-through. Now, this may not be a perfect graph. And for example, we don't really know how far this comes down exactly, or how far this one comes down. You could always plug in additional points if you want more information. So you can plug in values, in between 0 and negative 1, or in between 0 and 2. But this gives us a reasonable picture. Let's bring in a nicer picture just for reference. And you'll notice that my graph did look quite a bit different from this one. And this is because, again, we didn't really check to see how far this graph comes down in between these points. So in between negative 1 and 0, it actually doesn't come down very far at all. And in between 0 and 2, it comes down a little bit further. So if you want more details, you have to use more points. But the graph that we had a couple of minutes ago there was perfectly fine in terms of describing the basic behavior of the graph. One final thing to consider when graphing polynomials is something called local extrema, which basically just means local extreme values, which stands for local maximums and local minimums. So a local maximum point is a point on a graph that is higher than all the points right around it. Okay, so it may not be the highest point on the graph, but it's higher than all the points in its locality. And the local minimum is the graph that is lower than all the points immediately around that point. So it is a minimum of its locality. Now, we don't learn how to find maximums and minimums in pre-calculus. Usually that is taught in the first course of calculus, but we can estimate the number of maximums and minimums that we can have in a graph. So it turns out that if you have a polynomial of degree n, then the graph of p has at most n minus 1 local extrema. So for example, in this problem here, p1 of x is a fourth degree polynomial. So there can be at most 3 extrema here. Okay, 3 maximums and minimums. The next polynomial is a 5th degree polynomial. So in this case, we could have at most 4, right? Because it's 1 less than the degree. And in our last polynomial, this is a 4th degree. So once again, we can have at most 3. So we know this from what's above here, right? The local extrema polynomials. But that doesn't tell us how many we actually have. That tells me the maximum number that we can have. So what we're going to do is we're going to bring in the graphs of these polynomials, and we're going to count exactly how many local extrema it has in each case. So you should notice for the first one here, if you look at the graph, it actually has 1, 2, 3 local extrema, right? So it has 1 local maximum, and it has 2 local minimums. Okay, so that's consistent because we said it should have at the most 3, and in this case, it does actually have 3. In the next graph, you can see that we have a local maximum here and a local maximum here, and then we have a local minimum here and a local minimum here. So 2 local minimums and 2 local maximums, which brings us to a total of 4. And that is consistent because we did say it could have at the most 4. But in the final graph, this one here, you'll notice that there's only 1 local extreme value, and that's a local minimum, right? And so even though we could have had at the most 3, in this case, we only had a single one. So again, there's more information on how to find actual extreme values in calculus, but for now, we primarily rely on the graphs to help us see the extreme values. And that concludes this video lesson.